let's practice applying the open system entropy balance. In this problem, we're going to focus on a turbine in which steam flows through it. The steam enters the turbine with a mass flow rate of 4,500 kilograms per hour, a pressure of 60 bar, and a temperature of 500 degrees Celsius. As the steam exits the turbine, its pressure is lowered to 10 bar. In part A of this problem, we're going to assume that the entropy generated as the steam passes through the turbine is equal to 0. And so in that case, what we want to figure out is both the exit temperature of the steam and also the power, or the shaft work rate, that's extracted from the steam. In part B, we're going to take the shaft work value we get from part A, and we're going to take 80% of that, and we're going to use that as the shaft work in part B. And so based on that, we're then going to recalculate what the exit temperature of the steam is going to be, and also how much entropy is generated as the steam passes through this inefficient turbine. And so based on this text, what I want you to do now is pause the video here and draw a process flow diagram of this turbine. For this turbine, which is both adiabatic and in part A, well designed so that the entropy generated is equal to 0, we could describe it using the process flow diagram that's illustrated here, where the inlet steam has a mass flow rate of 4,500 kilograms per hour, inlet pressure of 60 bar, and inlet temperature of 500 degrees C. And the outlet pressure of the steam is going to be 10 bar as well. Now, as the steam passes through the turbine, shaft work will be extracted from it. And for the outlet steam, we technically don't know the mass flow rate, though that'll be pretty easy to figure out. But more importantly, we don't know the temperature of that outlet steam. And so in this problem, what we want to figure out is, in part A, for the case where the entropy generated as the steam passes through the turbine is equal to 0, we want to figure out the temperature and also the shaft work. And for part B, what we're going to do is we're going to look at the case where the efficiency of the turbine is only equal to 80%. And in that case, we want to then once again figure out what the temperature is and also how much entropy is generated by this process. Okay? And so looking at our process flow diagram, we essentially have three unknowns, which are the shaft work, the mass flow rate of the exit steam, and the temperature of the exit steam. And so that means we need three equations to solve for everything. Okay? Now, as far as assumptions that we can make for this system is, because the mass flow rate we're given, M1 here, isn't really changing, and we have an open system, we could probably assume that this system is going to be operating at steady state. The second assumption that we can make is that changes in kinetic and potential energy are probably going to be negligible compared to changes in temperature, pressure, shaft work, and shaft work. So EK and EP changes are negligible. The problem statement once again told us that the turbine operates adiabatically, so that means Q dot is going to be equal to 0. Okay. And then once again for part A, S gen dot will be equal to 0. Okay, so those are the assumptions that we could apply to the situation. And so now let's go ahead and apply them. Alright, so we're going to write out our balances. So we'll start with our material balance on the turbine. Inputs equal, or accumulations equal to input minus output plus generation minus consumption. Nothing's being generated or consumed. And this turbine's operating at steady state. Therefore, the input is going to be equal to the output, and that means, well, at least I'll say that the input's equal to M1, output's equal to M2. Therefore, M2 is just going to be equal to M1, which is 4,500 kilograms per hour. Okay. Alright, so for the material balance, we get that the mass flow rates are the same for both the inlet and the outlet. And that's going to be useful when we're manipulating our energy and entropy balances. Alright, let's now write out the energy balance. So we have the change in energy on the left-hand side, and we have energy transfer terms on the right-hand side, plus summation of alpha I, mi for the enthalpy, and then kinetic energy and the potential energy changes. Okay? On the left-hand side, not only do we're not really going to care about kinetic or potential energy, but we're not even going to be looking at changes in internal energy because this system's operating at steady state. Q is equal to 0 because the system's adiabatic. And once again, we're not really going to be looking at changes in kinetic or potential energy. So those are 0. And so our energy balance is going to reduce down to 0 is equal to the shaft work plus the enthalpy brought in by the inlet steam minus the enthalpy that comes out with the outlet steam. We know the mass flow rate, it's constant. And so what we have is shaft work plus m1 dot times h1 hat minus h2 hat. Okay. All right, and so here's our energy balance statement. This is what it reduced down to. And I'll call this equation 1. And in this equation 1, we essentially have two unknowns. We have the shaft work, and we also have this h2. And the reason those are the unknowns is, we're trying to figure out what shaft work is. But let me keep it in red. For H2, we know what the pressure is of the outlet steam, but we don't know the temperature. Okay, so if we only know one pressure, one variable, we won't be able to look up H2 directly from the steam tables. However, this all red and blue, for the inlet steam, we know both the temperature and pressure, and so we can look up H1 directly in the steam tables. Right? Okay, and so in any case, in our energy balance equation 1, we have two unknowns, but only one equation, so we can't really solve for everything yet. So what we should do at this point is move on to our entropy balance, and maybe that will give us information that will help us figure out H2 and shaft work. And so now let's apply our open system entropy balance. So ds dt is equal to the summation I equals 1 to 2 of alpha I mi dot si hat plus summation of whatever heat terms we have plus s gen dot. Okay? It's adiabatic, so we don't need to worry about heat. And for part A, we're going to assume that the entropy that's generated is equal to 0. And so our entropy balance is going to simplify down to m1 s1 hat minus m2 s2 hat. Once again, m2 is equal to m1, and so we could factor out m1, and we get s1 hat minus s2 hat is equal to 0. We could divide out the mass, so that's not even going to matter. And so what our entropy balance tells us is that the inlet specific entropy is equal to the outlet specific entropy. And I'm going to call this equation 2. Okay? And so this is a very useful relationship, right? Because if we know the T and P of the inlet stream, so we could look up the entropy just directly. Right? So that's how we could get S1. Then, because the entropy balance tells us that S1 is equal to S2, that information will allow us to then back calculate what the temperature 2 is. All right? And so I'm going to explain this in words. And so essentially, we know what the pressure is of the outlet stream. And we know that the entropy of the outlet stream, the specific entropy, is equal to the specific entropy of the inlet stream. And so, since we have those pieces of information, we should be able to figure out T2 in this manner by essentially interpolating our value of S2. Okay? And so here's the approach that we could take. What we could do is, since we know the temperature and pressure of the inlet stream, is we could just look up H1 and S1 directly from the steam tables. Okay. Once we have those values, we can then look up the pressure is equal to 10 bar section in the steam tables. And then we'll find temperature values that have specific entropy values that are above and below S2, which we know is equal to the S1 value. Once we find entropy values that are above and below our S2 value, what we would do is we would interpolate between those two entropy values to get T2. All right, and so once we have temperature 2, we could then use that temperature 2 value to interpolate our enthalpy value for H2. And once we have H2, we could then go back to our energy balance and solve for the shaft work. Okay? So, let's put this approach into action. All right? So what we're going to do is we're going to look at the steam tables for the enthalpy and entropy values. Okay? And so for the inlet stream, we know that the pressure is 60 bar, or otherwise known as 6 megapascals, and the inlet temperature is 500 degrees Celsius. What we don't know is if the steam that we're dealing with is saturated or superheated steam. But we could figure that out really quickly, and so what we could do is we could go to the saturated steam table. We could look up, and we're going to look at the table in which pressure is the independent variable. We go to the column in which the pressure is equal to 6 megapascals, and we see what the we could look, if I could get back there. We could look at what the boiling point temperature or the saturation pressure would be. Okay, so now that I'm back here, for 6 megapascals, the saturation temperature is 275.64 degrees Celsius. Our steam is at 500 degrees Celsius. So that means we're at a higher temperature than the saturated temperature. And so what we're dealing with is superheated vapor. Okay? So that means we should go to the superheated vapor steam table. We should go to the section for 6 megapascal. Look up temperature of 500, and then we should look up the enthalpy value and also the entropy value. Okay? And so we found our H1 and our S1 values, and so let's go write that down. So for the inlet steam, H1 is going to be equal to 3,422.2 kilojoules per kilogram, and S1 is going to be equal to 6.8803 kilojoules per kilogram. Alright, and from our entropy balance, we know that for the outlet, our entropy S2 is equal to the entropy S1, which is 6.8803 kilojoules per kilogram. Okay? Alright, so now that we know the entropy value for S2, and we know what its pressure is, which is 10 bar or 1 megapascal, what we should do is we should go to the 1 megapascal section of the superheated steam table, and we should look up entropy values that are above and below the value of 6.8803 that we have. So we're going to go to the steam table now. We're going to scroll to the 1 megapascal section, which is here, and we're going to look at the entropy column right here. I guess one of these. Alright, and so our S2 is 6.8803, and we find that at a temperature of 200, the entropy is 6.69, and at a temperature of 250, the entropy is 6.9. Right? And so those are slightly above and below our S2 value, so we could use these to interpolate. Okay? Going back to our work, at 200 degrees, the entropy is this. At 250 degrees, the specific entropy is this. We can interpolate between these two values. And the only unknown we have is T2. So if we solve for T2, we get 240 degrees, 0.4 Celsius. Alright, and so that is our temperature 2 value. Now that we know what temperature 2 is, we could go back to the steam table and we could once again set up an interpolation so that we could figure out what the enthalpy 2 value is. Okay? Alright, and so what we're going to do is we're going to look up enthalpy values at 200 and 250, and then we'll interpolate across them to get H2. So if we go back to the steam table, for 200 the enthalpy is this value, and for 250 the enthalpy is that value. Go back to our work, write down those enthalpy values. For 250, 2942.6 kilojoules per kilogram. Set up an interpolation. That's 200. Now that we know T2, for H2, this is our only unknown. So solve for H2. You get a value of 2920.5 kilojoules per kilogram. And now that we have H2, we could go back to our energy balance, equation 1. and just plug in for both H1 and H2. So what we get is minus 400 kilogram per hour, 3422.2 minus 2920.5 kilojoule per kilogram. And we're going to do a little bit of unit conversion to turn this into kilowatts. So our final answer is negative 627.1 kilowatts. Okay? And so this is a shaft work for the case when Sgen is equal to 0, or otherwise known, this is the maximum shaft work that can be generated by the turbine.